I'm so pleased to welcome you all here this evening, both our in-person audience and indeed our online audience. Tonight we have a special talk, The Rise and Fall of Radiator Foundries, a 2-century journey to casting radiators for today, with Nick and Annie Baylis, the owners of Castrads. I want to express our particular thanks this evening to heatinghelp.com, in particular to Erin Holohan Haskell for her help in promoting tonight's event. For those of you who are less familiar with the General Society, a brief introduction. The General Society of Mechanics and Tradesmen of the City of New York was founded in 1785, 238 years ago. We were founded by the skilled craftsmen of New York City. We are a non-profit organization that continues to serve and improve the quality of life for the people of the City of New York through our cultural and educational programs. These include our John M. Mossman Lock Museum, which you're also welcome to explore after the talk tonight. The General Society Library, of course, for our in-person audience, which is where we are based this evening. Our tuition-free Mechanics Institute, and I'm also really pleased that we have some of our students from the plumbing class here, along with their instructor, John Cattaneo, tonight, so I'd like to welcome them especially. And finally, our nearly €200 lecture series, of course, of which tonight's program is part of. Before I introduce our speakers, a quick reminder to mute your phones. We are so pleased to welcome Nick and Annie Baylis this evening. As I mentioned, the co-owner of Castrads. They're also normally based in England, so we're particularly delighted that they should be able to be here to speak in New York. Nick and Annie Baylis met while studying for their undergraduate degrees at the University College in London. After his master's degree, Nick began working in the family business, Castrads. In 2009, Mr. Baylis joined the company in Ms. Baylis joined the company, I beg your pardon, in 2018 after a career in translation and research, when the couple relocated to New York to set up Castrads North America. The process of refining their products for tomorrow's heating systems and sharing production continues to fuel their interest in cast iron radiators as markers of social and political change over the past 150 years. The couple now live in Stockport, England, with their 2 daughters. It is my huge pleasure to introduce to you Nick and Annie Baylis.
Thank you. Our story starts in Coventry, England. The year is 1995. I'm 9 years old, and my dad, Chris Baylis, that's him in the newspaper cutting right there, has a decade-old architectural salvage business called Reclaimed Building Supplies. It was a small firm that took salvaged building materials, cleaned them up, and sold them on to homeowners. On a Saturday, as a kid, I would help to clean up old bricks, remove nails from reclaimed oak beams, and, as the years went on, to refurbish antique cast iron radiators. Chris sold RBS around 2002 and moved to the Caribbean. But that didn't work out quite as he'd hoped. So he came back to England with a little less cash than he'd anticipated and found himself needing more. The thing that had worked best at RBS, better than the salvage, was selling new cast iron radiators. So that's what he did. He got in touch with an old contact, bought a container of radiator castings from the Far East, and set up shop in some barns just outside Manchester. And so Castrads was born. We make new cast iron radiators and refurbish old ones too. My name is Nick Baylis. I joined the business in 2009 after I finished my degree at UCL in London, which is where Annie and I met. I set up a showroom in London, built a small team there, and then started spending more and more time in Manchester, which is a 4-hour drive from London, as I took over the operational side of the business from my dad. After a couple of years of not seeing one another as much as we'd have liked, Annie and I decided to move out of London completely to a new life in the north of England. So in 2014, we packed our lives into a Castrads van and set off for our new home. We worked hard, built the business, and got married. For our first anniversary, we came here to New York, neither of us having ever been here before. I had no idea at that point, none whatsoever, that New York was the capital of the cast iron radiator world. I was completely green, but immediately after our visit, I started researching, frantically reading every single one of Dan Holohan's books, starting bit by bit to get my head around steam, which barely exists as a heating medium in Europe. But learn I did. And in 2018, we moved to Brooklyn. In fact, exactly 5 years ago today, by coincidence. We opened a very small showroom at 200 Lexington Avenue, just a short distance from here. And a little later, we took on 3,000 square feet of warehouse space at the Brooklyn Army Terminal in Sunset Park. And that, in brief, is why we find ourselves here today. So before Annie takes us back to 1995, we'd like to first thank Victoria, Karen, Angelo, and all of the magnificent team here at the General Society of Mechanics and Tradesmen for inviting us here today to speak. And of course, to the Holohan family for the work they do to create and maintain such a wonderful community of enthusiasts and engineers. We wouldn't be here talking to you today were it not for the lost art of steam heating. Tonight, we're going to tell the story of how we went from an architectural salvage business in England to onshoring the casting process for the first time in 50 years, to opening our new showroom in Manhattan's cast iron district. And for that, I'll hand over to my wife, Annie, who's become, like me, a radiator aficionado.
For my sins, yes. So, hi everyone. It's the mid-90s. IKEA has arrived in the UK, and there's 2 big home improvement shows on TV. Here you can see the Ground Force team, who were showing everyone how to transform their gardens. They were big fans of making raised beds with reclaimed railway sleepers, which was big business for RBS. Then we have changing rooms. They created a generation of DIYers and showed that there's no limit to what you can make out of a few boards of MDF. This was, and still is, the standard radiator in the UK. It's a simple steel panel hydronic radiator. You can buy them off the shelf in any DIY store or supply house. They're not made to last, but they're available in all shapes and sizes. They're cheap and easy to fit. Needless to say, they're not the most attractive options, and the changing room teams would throw an MDF cover over this as soon as look at it, and then probably paint it turquoise, add some fake fur and maybe some zebra print. It was crazy days. So we have RBS doing a roaring trade in railway sleepers, and there's also this burgeoning market for cast iron radiators, likely driven by an interest in restoring original features to Victorian and Edwardian homes, which is a large part of the housing stock in Britain. But were they in fact restoring original features? Not exactly. Central heating for the home took a long time to catch on in the UK. whereas they're so commonplace here, it wasn't widespread until 60s or the 70s, when cheap steel was having its moment, and hence these panel radiators are the norm. While in the US, cast iron radiators are commonplace, in the UK they're associated with grandeur. We're talking about museums, churches, and stately homes. And yet the foundations for central heating were laid in Britain at the very start of the Industrial Revolution. So what happened? Here comes a whistle-stop tour of how central heating first emerged. Throughout the 1800s, you have various engineers experimenting with methods of heating with hot air, hot water, and steam. Pre-Industrial Revolution, all of these are tentatively applied to horticulture. So heating hot houses for growing fruit and exotic plants. The key development towards domestic central heating is the Perkins high-pressure hot water system. It's patented by Annie March Perkins in 1831. Prior to that, you have William Strutt developing hot air heating in his cotton mill in Belper, Derbyshire, and that's the southerly-most marker on the map. And then Matthew Boulton and James Watt experimenting with steam at Twist Mill in Salford, and that's very close to where our base is in Manchester today. And these two are really key centres of technical innovation for the time. In 1792, William Strutt invented the cockle stove, a very economical type of stove, and he applied this heating technology to heating his cotton mills in Belper in Derbyshire. He later also heated the Derbyshire Infirmary with the same system. Hot air very basically is a furnace at the base of a building with an internal shaft that channels that hot air up through the building, and it's then vented into various rooms. Strutt was also a pioneer of fireproofing, so he started incorporating iron into the structure of his buildings. Key thing to understand is that textile mills are filled with cotton dust and fibers. They're highly flammable. Fireproofing is really vital. On the left here is Strutt's original timber-framed mill, which was destroyed by fire. He then rebuilt it in 1804 with this iron structure, which you can see on the other side. I think you can just about see the columns. This was the very earliest fireproof mill, and it's now a UNESCO World Heritage Site. In the face of the fireproofing problem, steam offers a very promising solution. And in 1799, steam engine pioneers James Watt and Matthew Boulton installed the first steam heating system at Twist Mill in Salford. It was one of Manchester's largest and most technologically advanced cotton spinning factories. Steam-powered textile mills had previously used exhaust steam for heating, so the steam is simply channeled around in big pipes. There's no pressure in the system. But Twist Mill is 7 stories high. It's only the second multi-story iron-structured building in Britain. It's cutting edge because you have a pressurized system, and it's sending all of that steam up several floors. Twist Mill also is the first to install gas lighting, and they also extend that to the surrounding streets. So it's like a hotbed of new scientific thinking. There's also obviously the developments in steam power and spinning technology that James Watt and Matthew Boulton are experimenting with. Twist Mill has since been demolished. It's not there anymore. The closest thing we do have is this diagram. This is actually by Neil Snodgrass. He was a Scottish early pioneer of steam. This is his mill in the far north of Scotland, but it's very, very similar to what Twist Mill had. But as I said, the big leap forward towards domestic central heating is the Perkins high-pressure hot water system. Annie March Perkins was born in Massachusetts, the same year that James Watt and Matthew Boulton are installing steam heat in Twist Mill. So it's a much later development. But while steam heat is really only workable in mills and manufactories where there's already steam power, Perkins hot water system developed in the horticultural and zoological hothouses. So Early installations are the conservatories at Hurlingham House, which is now, for any fans of the British royal family, it's where Kate Middleton plays tennis these days. It's a croquet club. Also various hothouses at Kew Gardens, and the very lucky elephants at Regent's Park get a Perkins high pressure hot water system. It moved quickly then into public buildings, the Bank of England, the British Museum, all sorts of churches. These illustrations show the closed boiler and the pipes that were called inside to heat the water. And then just at the bottom, you have what that actually looked like in the room, the heat emitter. It's a very rudimentary coil of pipe. It could either be hidden in the walls or it was covered by a decorative cover. But the water in these systems could get as hot as 287 degrees centigrade, which is 550 degrees Fahrenheit. And the pipes were known to fail at pressure, so there were some accidents. Between 1839 and 1841, there's a series of letters to the editor of the Times raising concerns about the safety of these systems. The Manchester Museum of Natural History was set on fire in several places due to overheated pipes. One textile factory in Manchester had a boiler explosion which caused £20,000 worth of damage, which was quite a lot of money back then. There are several recorded cases across the country, and the risk was indiscriminate. We have Camberwell Workhouse in London had pipework burst with much damage, and Lothbury Church where burst pipes scalded the charity children, poor little things. And the same thing is recorded happening in places like the Inner Temple in London, lots of VIP judges and barristers, also Marlborough House, which was the London residence of the Prince of Wales, and Strathfield Say, the country estate of the Duke of Wellington. So rich or poor, seemingly no one was safe. But it seems the letters came from an anonymous writer and may have even been a competitor of Perkins. Perkins responds to the letters in the Times with plenty of testimonials from high-profile, very happy customers. Accidents were relatively rare. Perkins continued to improve the technology, and there are Perkins systems still working today. But the perceived risk was enough to send insurance premiums rocketing, especially after a Perkins system actually exploded at the London HQ of a major insurance company, which is not the best PR, so, hard to come back from. So the system was expensive to install and to insure, and hot water central heating remained the preserve of churches, large institutions, private country estates, and wasn't refined for domestic homes until much later. In the UK, we tend to talk about church radiators, school radiators, hospital radiators, when what we mean is cast iron. In 90s Britain, then, we find frequent crimes against historic buildings in the form of steel panel radiators. A British businessman called Bob Staples is renovating his own home, this lovely Georgian villa. He wanted to use decorative cast iron radiators, but was having a hard time sourcing them in the UK and saw a gap in the market. Bob traveled to the east coast of America, visited salvage yards, and filled a shipping container with original radiators with the intention of having replica molds made based on those styles. Bob's company, Karen, bought replica ornate radiators to the UK market for the first time. When Castrads started in the early 2000s, Karen was the biggest competitor and had by far the largest range. But why go to America to fill a container with original decorative radiators? Well, America is squarely the birthplace of the cast iron radiator as we know it. Hot air central heating developed in the US in a similar way to the UK. Again, it's institutions like banks, hospitals, prisons, and textile mills that are the early adopters. As far back as 1812, Middleton Woolen Mill Manufactory in Connecticut was using exhaust steam, but it's a low pressure system. Here you have the Perkins high pressure hot water system. and those kind of pipe coils that I showed you that were the heat emitters on those systems. They're very basic. They're adequate for horticulture. They hadn't moved on much as they migrated indoors. And at best, you would be wanting to hide them. But Perkins had an apprentice who came over from Boston in 1837. His name is Joseph Nason. He spent years learning everything there was to know about high-pressure hot water systems, and then took his knowledge back to Massachusetts, where he installed one of his first hot water systems in a textile mill. That was Burlington Woolen Mill in Vermont in 1845. Nason's advances made it perceived to be, deemed to be, and actually safe enough that he won the heating contract for the White House in 1855, highest accolade. Right around the middle, the fourth one in here, this is the Gold's mattress radiator. That's patented in 1854 by Stephen Gold's. His safety valve brought steam heat into the home for the first time. He was based in Connecticut. Then you have the Bundy loop. Nelson Bundy, a New Yorker, patents America's first cast iron radiator in 1874. Joseph Nason had made a wrought iron version along the same lines in 1862. And then you have in 1877, the Bundy Elite, which is a decorative sectional radiator and what we would recognize as a cast iron radiator today. So that container load of ornate radiators will have been predominantly made by the American Radiator Company. They were established in 1892 when 3 major foundries merged. Between their founding and 1899, they bought up multiple radiator and boiler foundries in the US with the help of JP Morgan. One such foundry was the Titusville Iron Company, who made the very ornate radiators here in the General Society. Rather sweetly, the model is called Joy. Building on the heritage of high quality ornate cast iron established by the stove makers of Philadelphia and New York, they took the industry by storm and grew into a multi-million-dollar company with a global reach. The pinnacle of their prowess can be seen right around the corner from here, the famous American Radiator Company building, which was completed in 1924. And just to illustrate the quality of their castings, this is an American Radiator Company Rococo that we restored recently. This lives at the Norman, an apartment building on the Upper West Side, and would have gone in there when it was built in 1910. I hope you can see the detail here. These kind of very opulent apartments were built for the Gilded Age elite. They were stuffed full of mod cons and gadgets, and steam radiators of this caliber would have been a must-have. At the turn of the century, American Radiator Company were exporting their radiators around the world. You have UK contractors like H. Munzing, who were importing into the UK from the US. And the UK at this point has nothing like the quality that Arco are producing. So case in point, this is Leicester Cathedral, which in 2015 became the final resting place of King Richard III, more than 500 years after his death. It was a big story. His grave was discovered beneath a car park, and his tomb, which you can see here, now draws over 100,000 visitors every year to the cathedral, which prompted a large-scale renovation. Either side of this amazing tomb are 2 American Radiator Company National 4-column radiators, which is a very ornate design. We reconditioned these along with several others as part of the works. Those radiators are 115 years old, and they were cast in Buffalo, New York. Imagine how costly and complicated it was to have these shipped over to England 115 years ago. For me, this points to the quality of the product and the reputation of the American Radiator Company, that there was a demand to ship radiators across such distances for use in these kind of prestigious buildings. Similarly, we have Rochdale Town Hall. It was inaugurated in 1871 and is now a grade 1 listed building. Rochdale is a satellite town of Manchester. It was very significant, very wealthy mill town during the Industrial Revolution, which you can see from the opulence of the building. This is Wukash installing one of around 30 radiators that we restored as part of an ongoing renovation project on this building. This is an American Radiator Company Detroit plain radiator. So Leicester Cathedral and Rochdale Town Hall really illustrate how the US was a center of excellence in the field. We assume that there was nothing being produced in England that could compare. In 1897, you have Edith Wharton taking aim at fussy Victorian ornamentation and overuse of pattern. In her book on the decoration of houses, she proclaims that overlaying pattern is always a mistake. In 1922, then, Arco produces the Quarto, which is all straight lines, plain faces. It's marketed as simple and chic, and the advertising features ladies' boudoirs and views of the Arc de Triomphe. Then in the 1930s comes the Arco, a much thinner cast tube radiator. Here, advertising from the time demonstrates the size of the Arco compared with the 1890s Peerless at the back, and then the Quarto. And here are some Arcos that we restored at our customer's home in Bed-Stuy, Brooklyn. And you can see that they were much more modern and understated in their design. And now Nick's going to tell you about the legacy of the company.
So what is the American Radiator Company's legacy? Well, mechanization to start with. This patent, filed in 1888 by Joseph Bond, who was one of the founders of the precursor to the American Radiator Company, was the original nipple that joins sectional radiators together. And these nipples are used on sectional radiators to this date. We use them in our radiators, and also modern aluminium radiator producers use them, and so do modern steel column radiators. So this endures. And the sectional radiator, rather than the Bundy loop style, allowed for much more convenience in assembly, both in the factory and on site, meaning that very large radiators could be transported to site and joined in situ. And that is illustrated here by the picket fence. This picket fence, which is in fact made of radiator sections. And that was joined on site using threaded nipples. And this was the American Radiator Company's display at the Chicago World Fair in 1893, just 1 year after they were founded. Equally, they were true foundry masters. In the foundry world, speed is of the essence. Slow foundries just don't make money, but fast ones do. The Bryant molding machine, the patent for which is shown just here, transformed the speed at which sand molds could be prepared in a green sand foundry. And all cast iron radiators are made in green sand foundries. This machine, bought with great gusto by the American Radiator Company, changed their mold making capacity from 30 per day per worker to 250 per day per worker. However, above all else, the American Radiator Company were master deal makers. They bought up their competitors, they bought the rights to their machinery so that no other foundry could access their tech, and they began their expansion abroad to Europe very early on. In 1894, in response to the panic of 1893, Clarence Woolley, who was the American Radiator Company's secretary, traveled to Switzerland and made $50,000 worth of sales. That's $1.7 million worth in today's money, in just his first trip. pretty successful. By 1895, they were already showcasing their products through a showroom that they'd set up in London, and then soon after that, they started opening foundries across Europe. So this is a map of of radiator foundries across the States and Europe, and that's where they were at that point. There were also, I'm sure, some in Russia, but I'm afraid I don't know much about the Russian radiator market. The burgundy markers show American Radiator Company foundries, and you can see that there are a lot. There are at least 3 in America. There's 1 in England, 2 in France, 1 in Italy, 1 in Germany. The blue markers are other American-owned radiator foundries. And again, there are several in America, of course, but there's also the Crane Radiator Foundry in Ipswich in England. The orange markers show non-American radiator foundries. But you can see that clearly the frenetic market that existed was a result of the great energy with which the American Radiator Company came to the market. It was a very strong market. The cast iron was really the only type of radiator available at that point. And that drove technological advances that really hadn't been seen before in the heating industry. Fast forward to 1990. All of the major American foundries, and I do say major because I'm sure there must have been some small ones that still existed, but all of the major American foundries had ceased production, and all Western European nations, except Italy, had stopped making as well. In Eastern Europe, we find certainly at least 1 big foundry in Poland and at least 1 big foundry in Czech. Also still in Italy, but at this point as well in China. There started a radiator renaissance. And the markets for cast iron radiators at this point were North Africa, Southern and Eastern Europe, Russia, and increasingly China. But the foundries were set up for large-scale mass production. Northern and Western Europe was all about panel radiators by this point. There were a small number of large foundries, and those foundries produced a small number of models in high volumes. Tooling changeover was very expensive, which meant that there was very little choice in the market. And the route to market was from the foundry to a wholesaler, to a supply house, to a plumber, to the end user, and all of that meant that cast iron radiators became very expensive and unloved, except in this niche market. By 2015, as a result, all the Italian foundries had gone. They had moved their production to Turkey. Steel multi-column radiators had outcompeted their heavier, more expensive to manufacture cast iron counterparts. And so in 2015, we're left with very few foundries. There's 2 in Turkey. There are actually 2 in China. And in 2015, there was still 1 in Czech. And with the lack of competition, there's been no need to develop new technology, even though the foundry industry as a whole continues to make great strides forward. The few radiator foundries that exist today are using the same technology that the American Radiator Company did. They're just not maintaining it as well, because why would they? There's no competition. Here's how a radiator is typically made. A pattern plate is plunged into a box of sand. This is called the drag. This forms the bottom impression of the outside of the casting. A sand core is then placed into that void, leaving a small gap below it, which will be filled with metal. That's the yellow part in these photos. So you can see that's the drag. The yellow part here is the core, and you can see there's a gap here between the black sand and the yellow sand. That becomes filled with metal. That's the bottom half. We then place chaplets, which are small aluminium cylinders, on top of the core. And their job is to hold the core in place when the dense molten metal is poured in. And without them, the core floats to the top like ice cubes in a glass of water. And you can see the chaplets here. here, here. Another pattern plate is then plunged into another box of sand. This is called the cope, and that forms the upper outside surface of the casting. And the cope is taken a longer line, turned over and placed on top of the stack, which completes the three-part assembly. A hole is then cut into the uppermost part of the sand mold and molten iron poured into it. And you can see here, this is where there'd be a cope on top of this, and then the iron will flow into this part and then flow along the runner here, through the ingate and into the radiator section. Then the metal cools and solidifies. Goes onto a shakeout line which knocks off the sand, just like a big toasted sandwich, really. So once again, bottom black part is the drag. We then place the cores in the middle and place the cope on top. So drag here, cores on top, cope coming on to make the complete assembly. And here it is all together. And here is where the iron will be poured through, and then it goes along some runners through the ingates and fills the void where there is no sand. The metal cools and solidifies, the sand is knocked off, the metal parts are cut away from the running system, which is what we call the series of conduits that allow the metal to flow into the casting. Then the castings are shot blasted to clean them, job complete. Sorry, the slides have come out of order here. So there are issues with casting this way. Chaplets can cause cold lap, where oxidized metal meets fresh flow, and it's difficult to obtain counter-gravity filling in a horizontal mold. That's one of modern casting's core tenets. I realized that if we were to create a sustainable business, we needed to take control of our supply chain and own our filling system IP. So how do we do that? Well, we start with the casting. In 2015, I met a young product designer called Simon Evans. His first project was to design our column radiator range, which is called Mercury. It's an intentional nod to the greats that came before us, to the ARC Quarto, to the ideal standard neoclassic, which we find in Europe. And following this, Simon designed our Emmeline radiator, which you can see in the photo just there. It's available in 9 sizes and built on the foundations of the Peerless style. And he's now working on a new patterned radiator, which will be our take on the ornate Rococo style. In developing our own designs, we've focused on quality, not quantity. We're not trying to do anything new, we're just trying to do it well. Simon is today one of only 3 people in the world that I know of actively designing new cast iron radiators. And the second of those 3 also works for Castrads. In this photo, all of the radiators behind Simon are ones that he has designed from scratch. The Complete Casting Handbook by Professor John Campbell is the #1 textbook for any student of casting. In March 2020, I suddenly and unexpectedly found myself with a lot of time on my hands. So I read this book from cover to cover. In that book, I recognized all of the quality problems that I'd ever come across, both in our own castings and those that I'd seen in vintage radiators too. Although we hold them up as the gold standard, it's not true that older radiators were without flaws. I frequently see casting defects in old radiators, such as air bubbles, cold lap, and entrained sand. So I decided I'd get in touch with John. I emailed him on a Sunday morning and then left my phone inside while I mowed the lawn. When I came back into the house 15 minutes later, I had a missed call and a very excited message from John. I called John back, not believing my luck, and we immediately got working on designing a new filling system based on vertical casting and counter-gravity filling. This is Copenhagen. I took this photo the evening that we arrived there. It's August 2020 at this point. We're in Copenhagen because Denmark is home to a company called Disa. They make the world's best vertical molding lines. Similar to Bryant and the American Radiator Company, Disa have pioneered a faster, more efficient way to cast, helping foundries to make better quality castings quicker and more cost effectively. This is their factory where they make their molding lines. I took this photo in August 2020 when John, Simon and I met with the team. The guy in the checked shirt there, that's Per Larsen. He's the world leading expert on thin wall vertical casting, and of course an employee at Disa. We worked closely with Disa to simulate John's ideas. That's John's original sketch. You can even see his signature there. And to the right is a simulation that we ran with Disa to see whether or not his idea would work. The basic premise of our system is that of counter-gravity filling. It uses ferrostatic pressure to make a casting with laminar flow without entrained defects. So how do we do that? What does that mean? Well, we incorporate a basin at the top to contain the metal. It must be higher than the top of the casting. It's just like flushing a toilet. The iron then flows down the down sprue, let's start here, and across the runner, where it meets the spin trap. And the purpose of the spin trap is to take the first part of the flow, what's called the meniscus, because the meniscus of the flow is oxidized, and we don't want oxidation in the flow. That's where we get cold lap. That's where we get entrained defects, bifilms, in fact, John calls them. So 2 parts of oxidized iron meeting together is not good news. We don't want that. So we send it off to the end and we contain it in a spin trap, which acts a bit like a Dyson vacuum cleaner, sorry. It's the vortex, it creates a vortex. It also allows any bits of stray sand that might be contained within that running system to not go into the casting. We want the precious casting to be full of unoxidized, fresh iron. And that's how we do it with the spin trap. We then build back pressure. Once the spin trap is full, it builds back pressure, and we then start filling the void in the radiator section. So here there'd be a core again. So we're talking about a 2mm wall at this point, which is very, very, very thin. The back pressure allows the iron to rise through the casting, and as you can see, it starts cooling. The solidus is at about 1150 degrees Celsius, and at this point here, you can see it's not quite filling. So that's what we're up against. Can we get liquid iron all the way to the top of the radiator section before it solidifies? It's tricky. It's tricky. The vents at the top allow the air to escape as the void is being filled. So we needed to test this out. Chamberlain and Hill are a foundry in England's Black Country, so called because of the outcrops of coal in the area. It's where the early geologists found limestone coal, and iron ore in abundance, and where the British foundry industry was born. Chamberlain have two diesel lines, which until recently were full with turbocharger bearing housings. A single grain of sand left inside the cavity of their castings would cause them to lose their supply contracts. This is a far, far cry from the standards that we've had to accept from the world's few radiator foundries. The combustion engine will, sooner or later, be outlawed in Britain, and while that's devastating for many businesses, it gives us a unique opportunity to access an automotive quality supplier without having the volume that's normally associated with that industry. Pictured here is Rob Hayworth, this guy here. He is a brilliant engineer to whom we are indebted for his experience, his patience, his wit. Rob spent 2 years working with Simon, John, and I on trying to fill at 2 millimeters. He persevered where all others would have given up. We had misrun after misrun after misrun, until after the 22nd iteration to our running system, we did it. This is Simon and I holding the first radiator casting made in Britain since the American Radiator Company foundry in Hull, England, ceased radiator production in 1972. In actual fact, this was the worst yield that Chamberlain had ever made. That's to say that the proportion of usable metal per mold was very low. Only about 30%, I think, usable metal for each pound of metal poured in. So for commercial reasons, even though we'd proved it possible, we decided to up the wall thickness to 3 millimeters. Makes the whole thing easier, it improves the yield, and it actually reduces the cost to manufacture. But whether 3 millimeters or 2, it's still the best radiator casting that I have ever seen. And to put the thickness into perspective, an American Radiator Company quarto is usually about 4 to 5 millimeters thick. So we're still winning. But a radiator casting is only the first part. You then need to machine it to make it into a thing that will hold water. Enter Marco Zorzetti. Marco runs Gisetta, which is the company that his dad set up in the early 70s. His machinery is in every radiator foundry of note that is or has been in operation since the 70s. In 2020, I learned that a Czech radiator foundry was closing its doors, and I knew that they had some excellent Gisetta lines. So I made them an offer to buy the lines. And this particular line was originally made in the late 70s. It has operated in 2 Italian foundries, and then from 2002 onwards was used at Viadras in Czech, from where I bought it. Gisetta's machinery is the Rolls-Royce of the radiator world. They make incredible machines that automate every aspect of sectional radiator production. Not only cast iron, but also steel and aluminium. They're based in northern Italy. So in 2021, Marco and his team traveled to Czech. They dismantled this machine, they took it to their HQ near Milan and refurbished it completely, fitting new electronics, new motors, new pumps, until it was working as well as new. A 50-year-old machine made fit for purpose once again. And in June of this year, we brought it on 2 trucks from Italy to Manchester, England. This is the first time ever that one of Gisetta's machines has been installed in England, which is a fact that I'm very, very proud of. And here's what it does. Stage 1 is loading. Place the as-cast sections into a loading trolley. Stage 2 is cutting. A cutting tool mills a flat joining face onto each of the 4 openings of the section. And you can see that happening here in the left-hand photo. Then 4 threads are machined simultaneously, 2 right-hand threads and 2 left. Stage 3 is the flush. The swarf, that's the pieces of metal that are left in there from the cutting, that's removed through a pressurized flush. Stage 4 is assembly. So the milled and flushed section is then transported to the assembly station, where a nipple and gasket are placed between the partial assembly and the next new section, Assembly heads, that's these things here, then pass through the new section and rotate, engaging the nipples into the female thread of the two radiator sections, which are either side of the nipple. And because the threads are opposing, right-left pairs, the two sections are brought together to compress the gasket, which is in between. And stage 5 is planing. So lastly, the assembled radiator is pushed on along the platform before it's planed, where a cutting tool is drawn along the length of the section to remove any burrs, which leaves an assembled radiator ready to be painted. And here are the first two radiators off the line. The one closest to the window is 8 foot long, and it's as straight as an arrow, which is not an easy feat at that length. The tolerance on the machine faces is better than 0.01 millimeters, which is a quality that I've not seen on any other cast iron radiator. And the detail of the casting is second to none. They say that they don't make them like they used to. I believe that in this product, we're now making them even better than they used to. In Marco Zorzetti's words, remember Marco knows every single radiator foundry in the world, he said, "I think we can call this a very good radiator." This is our 16th year in business and our 5th in New York. We operate in the UK, across mainland Europe, we export to Australia and New Zealand, yet it's here in America, where I feel we do our very best work. Nowhere else do we have the privilege of refurbishing such storied radiators, such exquisite pieces of architectural heritage. Nowhere else is the history of our modern world told so completely through an object so seemingly mundane, so outwardly average as a radiator. And when we sell new radiators, no other systems treat them with such extremes. In fact, it's thanks to our moves forward with steam systems that we're able to recruit the next generation of leaders in our business and engineers. People like Robbie Merchant, who has helped us endlessly with researching this talk, and Jason Riley, who at 25 years old has just designed this, which is our next generation of one-pipe steam TRV.
A few years back, we decided to put the Manchester worker bee on our Whitworth wall stay, which you can see in the picture here. That was designed by Simon Evans, who you saw earlier, in recognition of the industrial heritage of our hometown. We wanted to acknowledge the technological progress made in places like Twist Mill, places which many take as the starting point for the early skyscrapers, including the American Radiator Building. In fact, Twist Mill's steam heat system actually used the structural cast iron columns as the steam risers, an innovation which every steam heat system relies upon today. We're following in a long tradition of cast iron and steam, and we're also delighted to now be based in a beautiful cast iron fronted building in Lower Manhattan, a part of the city literally founded on cast iron and steam.
We'll be holding the grand opening of our new showroom at 70 Thompson Street in Soho, New York's cast iron district, this coming Thursday, October 26th from 6 p.m. And we would love for you to join us. Thank you once again to the General Society of Mechanics and Tradesmen, to our friends and colleagues who've lived the stories that we've been able to tell tonight. And thank you for listening.
Nick and Annie, thank you both so very much. Thank you for telling us in such great detail the stories of some very good radiators. So thank you so much, really much. And just I want to reinforce that you have just been invited to a party on Thursday night. We'd love to take some questions, both from our in-person and online audience.
a great presentation.
Thank you very
When you refurbish a radiator, do you completely disassemble it?
Not if we can help it. So old radiators often have asbestos gaskets in. If we can leave those alone, we do. And to add to that, they were built so well, we don't need to. Taking them apart can be a real pig of a job.
Cause more problems than yourself.
And we can cause more problems than themselves. And they're great, you know, they're good for another 100 years. Why take them apart?
So I have a couple of questions about the technology that you're using in the casting of the radiators. How are you melting your iron, your cast iron? What sort of purity level are you starting with? Is this recycled material? And how do you get the cores out of the castings after they've been cast? And maybe you could describe briefly what a core is, because that wasn't explained in your lecture. Thank you.
So the metal is scrap. It all starts as scrap. And in fact, Chamberlain and Hill in Walsall use our scrap. So when we damage a radiator section, when we can't use a radiator section for whatever reason, we save it, we send it down to Chamberlain, they remelt it and turn it into radiators for us. It's usually about 98% scrap, sometimes as high as 100%, but there'll always be a metallurgist on site at every foundry, and he or she will measure the metal. If needs be, they will add some pig iron to the mix, which is virgin iron, if they need to. We are casting at about 4.1% carbon equivalent. So that's to say, that defines the viscosity of the melt. And we find that gives us about the right viscosity to fill the mold. And sorry, the core, how does a core come out? So a core is made of sand with a resin binder, glue. And there's two ways that you can set that glue. You can do a cold core or a hot core. In this instance, at Chamberlain, we're using a cold core, but elsewhere in other foundries that we work with, it's a hot core. If it's a hot core, it goes through an oven and it gets baked and comes out hard. But the resin is the thing that binds the sand grains together. How does that come out? Well, the resin breaks down. The temperature of the iron melts effectively the resin, and that can actually be a problem. So in our first run from Chamberlain, we were getting something like a 20% leak rate, which is terrible. Obviously, you can't work with that. And that was because we were using 2% resin content, which was too high. The advantage of using more resin is that the cores don't break, they're more solid. The disadvantage is that when the iron goes in, it burns the resin, and that creates gases, and those gases need to go somewhere. And so they go through the liquid metal. And when they go through the liquid metal, they create a porous, they create bubbles, exactly. And that can be a leak pathway. We dropped the resin content to 1%, much less off-gassing. It's called loss on ignition, LOI, much less loss on ignition, and the problem was solved. That was all we needed to do. How do we then get them out? Well, actually what you're left with is a fairly friable mix, which just separates, it just comes out. And so you send the radiator along it's called a shakeout table. And so this thing that just goes up and down, and it knocks them around a bit, and the sand will flow out freely until you then shot blast them. And again, it's a bit of a jiggle, and the stuff comes out. We then clean them with water.
Thank you. We have a few questions, online questions. First of all, Nick and Annie, could you please repeat the invitation details?
70 Thompson Street in Soho. So that's Thompson Street between Spring and Broome. Is that right?
Yeah.
Yep. Between Spring and Broome, Thompson Street, 6 p.m. to 9 p.m. on Thursday, October 26th.
And do people need to RSVP?
that would be helpful. Only because we've got a large pizza order, which Emily there has been taken care of, and we're just worried that we'll run out of
Reminded to up
pizza.
it.
Yeah.
Right. Well, I tell you what I'll do. I will shoot to both our in-person and online audiences an email tomorrow with the RSVP. So anyone who wants to attend, you can then correspond directly.
Wonderful. Thank you so much. That would be useful. But also, even if you haven't RSVP, please do come along.
Yeah.
Right. Well, there we go. Right. Back to the questions. This is from Stephen. When casting, how do the little AL spacers not leave a void/defect in the finished cast iron radiator? And he adds, my old Arco peerless radiators have no gaskets between sections. Am I just lucky they don't leak? And he also adds a further comment, he just had more information. My radiators have 1.5 NPT L/R threaded nipples, by the way.
So how do they not leak? Chaplets first, thank you very much. So how does the chaplets, it's very simple. Aluminium, you'll have to forgive me, I'm English. Aluminium melts at 800 degrees C, which is some number of Fahrenheit, and iron melts at 1400. We pour at about 1450 degrees centigrade, so that when the iron hits the aluminium, it instantly makes an alloy, and it's assimilated into the mix. This is also why we don't like to use chaplets, because it can be a point of failure. How does a radiator not leak without gaskets? Well, if it's got conical nipples, which you would know because it would have a threaded bar running through the sections, then that type of radiator does not use gaskets. It uses simply the compression. So you use a hydraulic press to press all of the sections together, and there's a double conical nipple in between each section, and you'd put some sort of paste on there, something like today's Pro-Dope or any sort of paste that they used to use. Press it together and then lock it in place using a threaded bar. However, this gentleman sounds like he has got threaded nipples, and if he's got threaded nipples, left-right threaded nipples, and he's got no gasket, I don't know.
Right. Well, thank you for giving your best shot. Thank you very much. We do a very good shot. Okay, another online question: do you restore 1906 cast iron American radiators?
100%.
Okay, well there you go.
Every day.
I do have a couple more online questions, but I do want to make sure, is there anyone in the audience who would like to? Okay.
I see you're showcasing lots of very colorful radiators.
Absolutely.
Mine was white. I didn't know they came in other colors. Do people order different colors from the factory or what?
The person best suited to answer that question is Katie. I was going to say Katie King, but actually Katie Dawson, because she just got married. So Katie, I wonder if you could take this question for us.
Hi, yes, they do. I think it came from nowhere really, but there was a pink radiator that was featured in the slideshow, which we did, I don't know where my colleague Pete is, we did it over a year ago, and everybody in the factory at the time, they were so used to selling grey radiators. That was the big one in England, grey. But I did it, and I got a lot of grief off everybody, but we did the pink radiator, and after that, pink radiators soared. So yes, coloured radiators have taken off massively. We've just done some brown radiators in England. They seem to be really taking off now as well. So people are getting more daring. It's always really interesting to see what's going through the factory. There's nothing that phases me anymore. So, and it's pretty much a case of any colour we can do it, as long as it's a paint that we know that works well. Yes. We actually use the proper paint. So if it's a Farrow & Ball radiator, we used Farrow & Ball paint, Benjamin Moore. Yeah, so, yeah.
But also, no, we wet paint rather than powder coat. We've done both. We find that wet paint gives us more flexibility.
It feels like everyone in the States tends to be quite used to, like you say, white radiators or often silver radiators, because the advice is often to paint it silver to keep the temperature down. And it's a real joy to be able to show people how to break free from silver radiators, and you can go any color you like.
Right. We have, I'm going to ask the two more online questions, and then we'll see if another in-person question. So here's the first of the online questions. What is the weight of new radiators compared to similarly sized ones from 100 years ago? This is from Barbara online.
It's a great question. It depends precisely when they were cast. Are we talking 100 years ago, or are we talking 120 years ago? Because there's a big difference. Kev, who's not here today, one of our colleagues, Kev, helped my brother Adam to remove some McKeesport radiators from a customer's house in Park Slope. And they were, I think, the heaviest radiators that I have ever, I mean, in terms of footprint, they were the heaviest radiators I have ever come across. I think they must have been ½ an inch thick. And, you know, we're now talking 2 millimeters or 1/16 of an inch, something like that. We're talking very, very thin these days. And it was all due to advances in casting technology. It's much, much easier to cast something thick than it is to cast something thin. And the American Radiator Company really pioneered that very, very thin wall casting. In fact, the American Radiator Company, I suspect, started using phosphorus, more and more phosphorus, when the 1930s hit. And it was a Great Depression, so we needed to reduce the cost of everything, economize. Phosphorus makes iron less viscous, so it will flow much easier into the mold. And so by upping the content of phosphorus, you can get thinner walls, but it also makes for a much more brittle iron. And I broke a customer's 1930s radiator whilst trying to refurbish it. And I'm sure that it wouldn't have broken had it not had that phosphorus in there. So how heavy is an old radiator compared to a new one? It depends. If it's older, it's probably heavier than today's. If it was 1930s, it's probably a bit lighter than today's. It also depends where it's made today. Chinese radiators have a high phosphorus content, which allows them to have thin walls. They're very light. Turkish cast radiators are not. They have a lower proportion of phosphorus, and therefore the walls are thicker, and so they're quite heavy. Ours, thanks to the vertical casting and the counter-gravity filling, we're managing to get somewhere in between.
Right, thank you. Before I ask the last online question, do we have another in-person question? Oh, we have a few, good heavens. Well, okay, if we'll talk, well, I'm certainly one person who I'm going to ask, because this is absolutely his field. It's one of our, John Catania, one of our Mechanic Institute's instructors. John.
Great presentation, thank you very much.
Thank you.
So if there's a thinner wall thickness on these radiators, is that a design consideration when trying to size a new radiator to an old radiator as a replacement?
Yeah, it's a great question, John. It introduces lag. The thicker the wall, the more lag there is. And what I mean by lag is the difference in time. So what you want is for the radiator to get instantly hot, because when it's as hot as the fluid inside it, it's at design temperature. If you've got a lot of metal to heat up, then you've got a period of time where it's not at design temperature, and therefore the heat output of that radiator is not what it's designed to be.
Thermal mass.
Exactly, yeah. So you've got inertia and you've got lag. Lag is efficient in terms of efficiency. Lag is bad, and so yeah, you want a thinner wall. A thinner wall is a good thing, but it can cause other problems. You're more likely to get a leak if you've got a thinner wall.
Well, I mean, I guess I was asking, Nick, I'm sorry, would you specify a larger, I mean, I guess surface area would be the same, EDR would be the same.
EDR is the same, yeah. Yeah, which means that once it's at temperature, it's equivalent. It doesn't matter whether it's a 2mm, a 4mm, or an 8mm wall thickness. Once it's at design temperature, it gives the same temperature.
Thank you.
Yeah, thanks, Tom.
Thank you. Okay, I am going to take the two people whose hands came up, but then Nick, I'll ask you if you would make your answers as brief as possible. Okay, I'm just aware that time is getting on. So, but I'd love to take these additional questions.
I don't know if this is a brief as possible kind of question, but I was wondering if you could describe the restoration process a bit more. You mentioned earlier that you don't typically, take them apart, but is your scope limited to the radiators themselves? Are you assessing the entire system in a home?
It depends where. Really, in New York, we have people, in fact, they're all there, who will come around to your home and have a look at your system. And what we will then advise is what we can and can't do. And 9 times out of 10, we're going to recommend someone who's great, like John, sat at the back there, to come around and do the work for you, who will be able to dramatically reduce your heating bills, who will be able to install thermostatic radiator valves, which will allow you to control the temperature in each room. We will supply, at a cost, of course, new valves, so you can have greater control and more aesthetically pleasing valves, in fact, like that. The refurbishment process itself is we remove the paint, we'll recoat them in whatever color you'd like. We can change the bushing sizes so that you can, if you need to, but yeah, we'll work with you to do whatever is needed, as much or as little. We won't do more than is necessary, but we will always make sure you've got a working system as well.
Okay. Oh, I think my question got answered by the way of the last question. But are those valves that are on the front of that radiator? What purpose do they do?
So the big valve at the bottom, the steam. This is a one-pipe steam radiator setup. The steam comes from the boiler through this pipe here, hits the valve here. This should always be fully on or fully off. Steam comes into the radiator, rises, goes across the radiator, fills the radiator with steam. The air that's inside the radiator exits through this air vent here. This thing here is a thermostatic radiator valve. And so this blocks the pathway for the air to exit from the radiator at a given temperature. So you set the temperature on that thermostatic radiator valve. You say, I want my room to be 72 degrees Fahrenheit. And when your room is at 72 Fahrenheit, that valve is closed and no air can exit from the radiator. And if no air can exit from the radiator, no steam can enter. And so that's in brief what those valves do. Oh, these things, these are wall stays. These just hold the radiator to the wall. Their function is simply to steady the radiator, make sure it can't move.
Just checking that it's on. This is not a design or manufacturer question, it's a market question. So for new radiators that you're producing, if not for a whole restoration project, let's say, what is the market for newly manufactured radiators? Is it, I mean, the balance between commercial, residential, and also geographic, just roughly?
Here in the States, again, the best person to answer that is Luke Watts, who's sat right there. What would you say, Luke?
So I'd say, so for us in the States, predominantly we are servicing the residential market. We do work with some commercial buildings where we'll stick radiators in or even refurbish radiators, but predominantly we are working with residential end users, plumbers, heating engineers like John, and architects and designers. As far as the split around the country, we are very much in New York, and I'd say around 60% of the business we do is here because the market is so large here. Every building you walk into, you see a cast iron radiator. As Nick explained in his speech when he first came in here, it's a very niche product in the UK, whereas here it's commodity. But we do a lot, surprisingly, on the West Coast as well. San Francisco's got steam systems as New York has, and a lot in Detroit, Michigan, and areas like that as well. No, unfortunately. I mean, the odd. We've done some large houses, new houses that are built. We're doing one in the middle in Detroit right now, which is a large building. But most new buildings, unfortunately, nowadays they are, especially in the States, they're leaning towards or being pushed towards forced air, which we try and recommend against, but we don't like forced air. But I hope that answers the question.
Thank you. This will be the final question of the night for the program, not to say that you won't be able to ask the Castrad team many questions afterwards, and indeed at the showroom on Thursday, but this is the final question. Is there a difference in using a radiator for 2-pipe stream system versus 1-pipe systems?
Yeah, it's all in the valves. It's the same radiator, but it's all in how we set up the valves and the bushings. It's the photo there is a 1-pipe steam system radiator. In a 1-pipe steam system, as the name indicates, steam comes in and the condensate flows out through the same pipe. In a 2-pipe steam radiator, the steam enters through one valve on one side of the radiator usually, and exits. The condensate exits through a steam trap, which is often on the other side of the radiator. With a 1-pipe steam radiator, you're going to have a bigger valve. So you can see this is a very large bore valve. That's actually a 1¼ inch valve. With 2-pipe steam radiator, because you're splitting the steam from the condensate, you can have much smaller pipes. So you'd often have a 3/4 supply and a 1/2 inch return on a 2-pipe steam radiator.
Terrific. Thank you. Thank you. Thank you so much. Nick and Annie, I want to thank you so much for taking us through the history of radiator foundries with such eloquence and expertise. We're absolutely delighted that you could be here this evening to share your knowledge, and we wish you great success with the showroom and all Castrad projects. To say a few words is Victoria Dangle, our Executive Director.
Thank you so much. Thanks for having me.
Yes, and thank you, Nick and Annie. Yeah, as Karen said, so comprehensive, so wonderful. What went into that presentation was evident, but that presentation was the culmination of so many years of passion, which I just have to address with your company and the employees. I know, and I've never seen the consistency of that passion, the excitement of Katie, Robbie, Zico, and Luke. I've never seen anything to that degree. And I just want to go back to last summer when they found out about a library on the 4th floor in our heating museum. That's for another conversation with the heating museum. It was August, it was hot, there was no air conditioning, and they sat there for hours and read. I checked up on them at one point, and there was no air in the room, and they were just gobbling up every bit of information, and I have the photos to prove it, it's true. And I just love the excitement and that you bring this subject to life, and and your customers are very lucky to have you. And I know how much Dan Holohan has meant to you in your life, but yes, our wonderful Dan Holohan, but your work tonight was in the vein of his presentations, the passion, the excitement, and making it all easy for us to understand. So congratulations, and we're wishing you every success. All right, thank you.
Thank you so much.
We just want to present you with a little memento of tonight, the poster. And I just want to remind you of our lecture coming up on Monday. And note, it's Monday, not Tuesday, and that's going to be about Greenwood. Brooklyn Arcadia, Art, History and Nature at Majestic Greenwood. I do hope you'll join us for that. Thank you to our online and in-person audience for joining us this evening. I invite our in-person audience to join us for a glass of wine, and I will be sending out that party invitation tomorrow. So many, many thanks to Nick and Annie and to the Castrads team. Thank you so much.